Second topic of the chapter, electrolytic conductance. So what is conductance first? Conductance is defined as reciprocal of resistance. So class, we can write C equals to 1 by R. And class, in this topic, units are very important. So resistance is ohm. So 1 by R is ohm inverse, or also called mho, MHO, or also called Siemens. All are in use. Then after conductance, we come to specific conductance. Here we will have to do some derivation. Class, from physics we know R equal to rho L by E. The next step, I can write rho equals to R into A by L. Taking reciprocal. Class, remember, rho is your specific resistance. So if I take 1 by rho equals to 1 by R into L by A. Class, if rho was your specific resistance, then 1 by rho becomes your specific conductance denoted by kappa equals to 1 by R. You know, it's your conductance into L by A. Let us make equation number 1. Continuing further, if L equals to 1 centimeter and A equals to 1 cm square, then kappa becomes equal to C. So class, how can you define specific conductance? Specific conductance, okay, let us do some more here with the diagram. Now listen carefully, this is the diagram of any electrolysis taking place. Let us take length of the electrode is 1 centimeter and breadth also 1 centimeter, and same here 1 centimeter, and distance between them is also 1 centimeter. Two plates are being taken. Length is 1 centimeter, breadth is 1 centimeter, and the gap between them is also 1 centimeter. So class, we can very well say that liquid present here is 1 cc, 1 centimeter cube volume. So class, we can very well define specific conductance. Specific conductance is defined as conductance of 1 cc of an electrolyte. Specific conductance is defined as conductance of 1 cc of an electrolyte. Class, in any electrolytic cell, L and A, that is length of the rods and area of cross section of the electrolytes, are always same, hence also called cell constant. Cell constant, and it is symbolized as G star. So the next step, we can write equation number 1 as kappa equal to C into G star. That becomes your expression number 2. In the next topic, we are going to take molar conductance. Molar conductance is defined as lambda m. Symbolized as lambda m. How can we define it? It is conductance of solution in CC containing 1 gram mole of the substance. So class, we can write here lambda m equals to kappa. Class, remember what is kappa? Kappa is conductance of 1 cc of electrolyte multiplied by volume in cc containing 1 gram mole. So it is conductance of solution in cc containing 1 gram mole of the substance. So cc is the volume of the solution, right? So class, in the next step I can write lambda m equals to kappa into 1000 upon C. And what is C? C is your molarity. Class, before going to that, let us again come here. We have taken unit of conductance as ohm inverse. Let us find out unit of specific conductance. Unit of kappa. Class, remember what is conductance? Ohm inverse. And length is determined in centimeter and area is determined in centimeter square. So centimeter goes with centimeter and we are left with 1 centimeter here, that comes up cm inverse. So kappa is ohm inverse cm inverse. The same way, we can here also find out ohm inverse cm inverse multiplied by 1000. Remember it is in cc. So centimeter cube upon mole. So if we multiply centimeter cube with centimeter inverse, we get cm square. So unit of lambda m equals to ohm inverse cm square mole inverse. Plus one more topic remains, that is your equivalent conductance. Noted as lambda eq. So again I will write same thing here. Conductance of electrolyte. Class, make it here electrolyte. Not solution. Electrolyte. So same here. It is conductance of electrolyte in CC containing 1 gram equivalent of the substance. Same. Molar conductance, equivalent conductance are more or less same. Here we are taking 1 gram mole and here we are taking 1 gram equivalent. So straight away we can find out the formula lambda eq equal to kappa into 1000 upon n. And what is your n? N is your normality. And unit ohm inverse cm square equivalent inverse. Students, our next topic is molar conductance at infinite dilution. Class, you know very well, lambda m denotes molar conductance and this sign of infinity indicates molar conductance at infinite dilutions. Class, we have already studied that whenever we put any electrolyte in water, it gets dissociated. So it is believed that at infinite dilutions, whatever may be the electrolyte, strong electrolyte or weak electrolyte, they almost get 100% dissociated. So to find out the conductance of any electrolyte, if infinite dilution concentration, that is at infinite dilution, the molar conductance can be accurately calculated. So that's why we are going to study molar conductance at infinite dilutions. Next topic is behavior of electrolytes at infinite dilutions. Class, here we have to study two graphs. Let me make the graph. this curve is meant for strong electrolytes, and this curve is meant for weak electrolytes. Weak electrolytes. Listen carefully the entire lecture, because this both the graph you have to write in your fair register. Let us first talk about strong electrolytes. What are strong electrolytes? In class 11, in chapter ionic equilibrium, you have already studied that those electrolytes which are almost dissociated in water are referred as strong electrolytes. So class, we are going to plot molar conductance of strong electrolytes against root C. C is your concentration, molarity. Class, as you know that strong electrolyte is already dissociated, if that is around 90, 97, 98, 99% they are already dissociated. If you put more water to it, then since they are already dissociated, very less ions are left, so the conductance behavior rises very slowly. So we can plot the graph. So we get the curve like this. And since you are all student of maths, if you get a curve like this, I can very well extra plot the curve and let it comes to here. So here root C is 0, concentration is 0. It means the electrolyte is infinitely diluted. So this indicates molar conductance of strong electrolyte at infinite dilutions. So class, with the help of this curve, listen carefully, with the help of this curve, we can very well calculate molar conductance at infinite dilutions for strong electrolytes, because the curve can be extra plotted. Now let's talk about weak electrolytes. As we all know that weak electrolytes do not dissociate completely. Their dissociation is either 10%, 20% or 25%. So when we put water to it, they start showing higher conductance. The reason is that the electrolytes get dissociated more and more, so their graph rises steeply. But when they approach infinite dilutions, the curve rises very sharply and it becomes parallel to the axis, y-axis. So this is a curve meant for weak electrolytes. What you find here, when we further dilute weak electrolytes, since they undergo dissociation, so their conductance increases many-fold. As you see, the graph is rising rapidly, and when it approaches at infinite dilution, the curve rises so sharply that it becomes almost parallel to y-axis. Now class, why we are studying both these graphs? The application of these two graphs is that in the case of strong electrolyte, listen carefully, molar conductance of strong electrolyte at infinite dilutions can be calculated with the graph easily. But in the case of weak electrolyte, the curve rises sharply, and since it becomes almost parallel to y-axis, the curve cannot be extra plotted, because you see the two lines are running parallel to each other and they are going to meet at infinity. So that's why we are never able to extra plot this thing. Here we have been able to extra plot, but here we are not able to extra plot. Therefore, molar conductance of weak electrolyte cannot be calculated graphically. So these two graphs should come in your register. You will explain both the things. In strong electrolyte, I repeat again, in the strong electrolyte, since they are almost dissociated, if we further dilute them, they show very minimal increase in their conductance behavior, and hence the graph is extra plotted, and hence we can very well find out molar conductance at infinite dilution for strong electrolyte. But in the case of weak electrolyte, since they are very less dissociated, as we go on diluting them, they show manifold increase in their dissociation of ions, and hence manifold increase in their conductance behavior. And whenever they are approaching infinite dilution, the curve rises sharply and it becomes almost parallel to y-axis, and hence the molar conductance of infinite dilutions molar conductance at infinite dilutions for weak electrolyte cannot be calculated graphically. So these are two major points. Class, in the last session, we just now studied that it is impossible to calculate molar conductance of weak electrolyte. So there was a problem how to find out the molar conductance of weak electrolytes. For that, Kohlrausch law came into existence. What it states? It states that at infinite dilutions, every ion makes its definite contribution towards conductance of electrolytes. Or, in simple terms, you can say at infinite dilutions, current carried by any electrolyte is equal to sum of current carried by cations as well as anions. Let's take an example. Molar conductance of NaCl at infinite dilutions can be given as molar conductance of sodium plus ion plus molar conductance of chloride ion. So if we add conductance of sodium plus ion and conductance of chloride ion, we can very well get molar conductance of NaCl. Class, the law is very important. So let us solve one very simple numerical on this. Find lambda m infinity for aluminum 3 plus ions if lambda m infinity sulfate ions equals to 200 ohm inverse Cm square mole inverse, and lambda m aluminum sulfate as a whole has been given to you 858 ohm inverse Cm square mole inverse. So class, first we'll take aluminum sulfate, we'll break it like this. Lambda m infinity Al2SO4 whole thrice can be shown as lambda m infinity aluminum ion plus lambda m infinity sulfate ions. But class, remember how many aluminum ions are there? So 2. So you have to multiply the molar conductance by 2. Similarly, how many sulfate ion? 3. So you have to multiply by 3. Now I am going to put in the value. Aluminum sulfate 858. Aluminum we are supposed to find out, so let it be 2x, 2 and aluminum x plus 3 into sulfate ions 200. Open it. 858 equals 2x plus 600. So 2x equals to 258. So x will be equal to 129. So we can write answer lambda m infinity aluminum 3 plus ions equals to 129 ohm inverse Cm square mole inverse. So class, in this way we will be solving numericals of Kohlrausch law. The next topic, we are going to take up application of Kohlrausch law. Class, there are two applications for Kohlrausch law. Number one, calculation of molar conductance at infinite dilution for weak electrolyte. Class, remember, with the help of graph, we are able to find out the molar conductance of strong electrolyte only. We are not able to find out the conductance behavior of weak electrolyte. But Gauss law helps us in getting molar conductance of the electrolyte, and we can also calculate degree of dissolution of the electrolyte. So these two are the major applications of Gauss law. We are going to take one numerical on this. First is find molar conductance in finite dilution for acetic acid, and these three data has been given to you. Molar conductance of sodium acetate has been given to you. Molar conductance of HCl has been given to you. Molar conductance of NaCl has been given to you. Class, these data are of myself. Please don't quote anywhere. We are just going to solve the numerical. Don't concentrate on the data itself. It is not required, but yeah, we are going to solve it. So, Koldon's suggested that these are all strong electrolytes. That's why we are able to find out their molar behavior, molar conductance behavior. But acetic acid, you have studied in class 11, acetic acid and ammonium hydroxide, these are the two weak electrolytes which you have studied. So, Koldon's suggested that by simple addition and subtraction, we will be able to find out molar conductance of acetic acid. Class, how? Let us see here. Class, can I write like this? Lambda m infinite dilution sodium acetate plus lambda m infinite dilution HCl minus lambda m infinite dilution NaCl. Now let us just dissociate it. In the next step, I can write lambda m infinity acetate ion plus lambda m infinity Na plus ion plus lambda m infinity H plus ion plus lambda m infinity chloride ion, and now negative sign lambda m infinity Na plus ion and lambda m infinity, should be minus. Chloride ion. Class, let us make equation number 1. What we have done in the next step? We have just dissociated all these strong electrolytes. See, sodium acetate, acetate ion plus Na plus ion, HCl, H plus ion and chloride ion, NaCl, Na plus ion and chloride ion. Plus, sodium plus ion and sodium Na plus ion, here it is positive, here it is negative, they get cancelled. Then lambda m chloride ion positive, lambda m chloride ion negative, they also get cancelled. So class, what I am left with? Acetate ion and H plus ion, and when you add these two, you get your acetic acid. So this was the application of Koldon's law. He simply said by simply addition and subtraction, we are able to find out if, I repeat again, if molar conductance of strong electrolytes are known, which are common to the weak electrolyte, then by simple addition and subtraction, we can very well find out molar conductance behavior of weak electrolyte also, as you have seen in this following equation. Now I am going to putting the value in equation 1. Sodium acetate 300 plus HCl 100 and then minus NaCl 50. So 400 minus 50 gives you 350 ohm inverse Cm square mole inverse, and this is your lambda 50 acetic acid. So that was first part done. Now we are going to take the second part. Calculate degree of dissolution of acetic acid if 0.1 molar acetic acid gave molar conductance equals to 30 ohm inverse Cm square mole inverse, and given lambda m infinity acetic acid. This is already calculated previously before, 300 ohm inverse Cm square mole inverse. Class, the formula he gave, calculation of degree of dissolution of electrolyte, as follows. Alpha, you all know DOD equals to molar conductance at C concentration upon molar conductance at infinite dilution. So class, molar conductance at C concentration, 0.1 molar concentration is how much? 30. So I write here 30. And molar conductance at infinite dilution is how much? 300. Divide 30 by 300 gives to 1 by 10 and 1 by 10 is 0.1. So we can very well find out degree of division is 0.1, and if I multiply by 100, I get 10% dissociation. One thing more, that was first part. Second part, calculate Ka. Class, this Ka word came in solution chapter also, and it is coming from Oswald dilution law, class 11. What is the formula? Ka equals to C alpha square, dilution constant of weak acid. Concentration is how much? Concentration is 0.1 multiplied by again alpha square 0.1 into 0.1. So this gives you 10 to the power minus 3. So class, these were the two major applications of Losch law. First, finding molar conductance of weak electrolyte and finite dilutions with the help of molar value given for molar conductance of strong electrolyte. If we know the value of strong electrolyte having common ion with weak electrolyte, we can very well calculate molar conductance of weak electrolyte also. And the next step we understood how to find out degree of dissolution of weak electrolyte.